AI has done a lot of awesome things in recent years, from defeating the human champion at Go to, of course, the hugely popular and actually entertaining ChatGPT. This has led some to become concerned about what will happen as AI becomes better and better, and some have even expressed concern about AI overtaking humanity. Now, those who make this claim aren't necessarily envisioning something like the Matrix or the Terminator. Rather, the threat is more existential and philosophical. It cuts the heart of what it is that makes us human and whether we are special or unique in any way. And this is an idea called human exceptionalism, which says that humans are different from other animals or have greater moral value. In this video, we're going to explore whether humans are different from AI when it comes to intelligence, and whether AI can surpass humans on all mental tasks. For instance, Google's Ray Kurzweil coins the term AI singularity to describe when, quote, human beings are no longer the most intelligent or capable type of entity on the planet, and he believes this will happen before the century is over. Others agree. Physicist Stephen Hawking warns that the emergence of artificial intelligence could be, quote, the worst event in the history of our civilization. Henry Kissinger, former Secretary of State under 2 US presidents, warns, quote, philosophically, intellectually, in every way, human society is unprepared for the rise of artificial intelligence. And entrepreneur Elon Musk says AI is humanity's, quote, biggest existential threat. Of course, for this to happen, machines will need to be more intelligent than humans, and not everyone thinks this is possible. For instance, another famed physicist, Roger Penrose, who actually co-authored with Hawking, thinks differently. He writes that computers are just following simple mechanical rules and as a result do not understand what they're doing. And he famously wrote, quote, intelligence cannot be present without understanding. No computer has any awareness of what it does. The director of the Johns Hopkins Robotics Lab agrees, claiming that AI does not display human traits and robots will not, quote, be able to exhibit any form of creativity or sentience. And Microsoft's CEO Satya Nadella wrote, quote, one of the most coveted human skills is creativity, and this won't change. Machines will enrich and augment our creativity, but the human drive to create will remain central. So who is right? Will AI be able to do everything humans currently can just as well, if not better? Or is there something fundamentally different about humans that AI cannot replicate? That's what we're going to be exploring today. To state what is probably overwhelmingly obvious to many viewers, what we call AI are just software algorithms that are run on computer hardware. These algorithms are fundamentally step-by-step procedures written in computer code. Computer hardware executes the steps in sequence. So as a result, computers can only execute algorithms, or what are sometimes called computable tasks. Now, right off the bat, this limits what computers can do. There are many tasks proven to be non-algorithmic, and thus beyond the capacity of computers to solve as a matter of principle. For instance, Alan Turing and Alanzo Church both published on what is called the halting problem, which proves that there is no algorithm that can take in a computer program and an input and tell you whether the program will run forever or halt given that input. This shows that there are some easily mathematically definable functions that are not computable. A generalization of this comes in the form of Rice's theorem, which proves that all non-trivial semantic properties of programs are undecidable and thus uncomputable as well. What does this mean? Well, a semantic property of a program is a property about its behavior or its meaning. For instance, an example of a semantic property is to say that a program prints hello world at some time when it is running. This is differentiated from what is called a syntactic property. So a syntactic property is a property about the syntax, which would be like saying something like the program has a line that says print hello world. Now, while this line does indeed print hello world, the difficulty comes in when you look at other possible lines, such as something that says print x, where x is a variable in the program that is assigned and updated as the program executes. Rice's theorem proves that it's impossible for a computer to decide what an arbitrary program does by looking at syntax alone, unless of course that property is either true for all programs or false for all programs. As a result, it is provably impossible to write a program that takes in another program and definitively tells you whether or not that program has a bug. Now, what is interesting about this is Rice's theorem was proved by Henry Gordon Rice in his 1951 doctoral dissertation, a year after Turing published his influential and widely read paper, Computing Machinery and Intelligence. This is the paper where Turing introduced the famous Turing test. But this paper also discussed Turing's responses to several objections to the idea that machines could be intelligent. One of them is the mathematical argument. Turing acknowledges that there are limits to what computers can do, but finds it unconvincing to think this means we can rule out machines being intelligent. He writes, quote, although it is established that there are limitations to the powers of any particular machine, it has only been stated, without any sort of proof, that no such limitations apply to the human intellect. But of course, Rice's theorem tells us, which Turing was clearly unaware of at the time, that computers are limited in their ability to determine semantics, referring to meaning and behavior. And this semantic versus syntactic, or meaning versus mathematical distinction is key to answering the question of whether we as humans are more than just machines. So with this background, we should ask whether humans have properties that are non-algorithmic or non-computable. If so, then we can conclude AI will never be able to do what humans can, at least in some areas. Electrical engineer and computer scientist Robert J. Marks, who I met at a conference recently, identified 3 non-computable human traits to argue AI will never be able to do what humans can, and these are sentience, understanding, and creativity. Let's go through each of these briefly and see what his arguments are. We'll start with sentience. A component of sentience is qualia, which refers to our subjective conscious experience, often in response to stimuli. Philosopher Thomas Nagel writes about this in his famous 1974 paper, What Is It Like to Be a Bat? He writes, quote, "If we acknowledge that a physical theory of mind must account for the subjective character of experience, we must admit that no presently available conception gives us a clue how this could be done." This was also illustrated in a thought experiment by Frank Jackson called Mary's Room from a 1982 paper titled Epiphenomenal Qualia. It goes like this. Mary is a brilliant scientist who, for whatever reason, is forced to investigate the world from a black and white room via a black and white television monitor. She specializes in the neurophysiology of vision and acquires all physical information there is to obtain about what goes on when we see ripe tomatoes or the sky, and use terms like red and blue and so on. She discovers, for example, just which wavelength combinations from the sky stimulate the retina and exactly how this produces via the central nervous system the contraction of the vocal cords and the expulsion of air from the lungs that results in uttering the sentence, "The sky is blue." But what happens when Mary is released from her black and white room or is given a color television monitor? Does she learn anything new or not? Jackson thinks she does, and as a result thinks the physical reduction of consciousness fails. Answering this question of why we have a conscious experience at all is called the hard problem of consciousness by philosopher of mind David Chalmers, who I got to talk to at NeurIPS a few years ago. The main point in all of this is to say there is something about the experience of being a person, of living and existing as a person, and this is something a computer cannot grasp, the same way we have no idea what it is like to fly around as a bat using echolocation. This is echoed by Hubert Dreyfus's book, What Computers Can't Do, followed up by the aptly named What Computers Still Can't Do. To Dreyfus, the mind is nothing like a digital computer, and if it has any qualia or subjective experience at all, which is highly dubious and would be pretty much unverifiable anyways, it would certainly differ from our experience as humans for several reasons you should consult Dreyfus on. Let's move on to understanding. John Searle famously proposed his Chinese room thought experiment in 1980, attempting to refute the theory that human minds are computer-like information processing systems. So what Searle is trying to do is say, look, computers can imitate, but they cannot have actual understanding. The argument goes like this. Searle is alone in a room following simple rules for responding to Chinese characters that are slipped under the door. Now, Searle understands no Chinese, and yet by following the rules in a computer program manipulating characters, he can basically send appropriate strings of Chinese characters back out the door. So this leads those who are outside of the room to mistakenly suppose that there actually is a Chinese speaker in the room. And the point of this is, while from the point of the view of the person on the outside, Searle understands Chinese, all he's doing is really just taking symbols, following some steps, and writing symbols back. He has no idea what these characters mean or how they relate to the world. This again goes back to that syntactic versus semantic distinction we talked about earlier. Now, Searle concludes that while computer programs such as ChatGPT may make it appear that they understand language, it may not produce real understanding. Now, Searle claims this thought experiment shows computers have no understanding of meaning or semantics. They just manipulate symbols syntactically. As a result, the Turing test is inadequate. And as an aside, I should mention Kotaro Uchikoshi incorporates and engages with quite a few of these thought experiments in his work. So definitely check out his work like AI the Somnium Files or the Nonary games if you like escape room puzzles and really interesting writing. Anyways, the point in all of this is to say that even models like ChatGPT, which I'd say have passed the Turing test, they just only manipulate symbols. These models have no idea or understanding of what these symbols actually mean, and no experience of the world that could impart meaning on these symbols, even if such a thing was algorithmically possible. And as a result, to claim that AI based on digital computer hardware really understands or knows anything makes a category mistake. Just as a recipe does not know how to cook, ChatGPT as a model does not understand anything about what it's doing. Here's an analogy that illustrates what I call the symbolic semantic gap. And I believe I got this analogy from Antony Flew, but I went back through some of my books and couldn't find exactly where I found it. So suppose you went to a basketball game and you attached a brain scanner to each of the players and recorded all their brain data during the game. From this brain data alone, could you then deduce the rules of basketball? No, I mean, how could you ever expect to deduce the rules of basketball without knowing what these signals correspond to, without knowing what these thoughts are about? We see this in practice by watching ChatGPT play, or I should say try to play, chess. I'll provide a link in the description, but it's pretty entertaining to watch, to be honest. Now, ChatGPT was trained on a lot of text, and this text includes data from chess games in this sort of text-like format. And ChatGPT has been presented with more text data representing chess games than any human could possibly play or read in their entire life, than any human could ever hope to read or play in their entire life. And yet, even with all this data, ChatGPT cannot learn the rules of chess. It still makes illegal moves, and it still cheats. So being presented with a lot of data isn't enough to guarantee learning or understanding, even at a basic level. Let's move on to creativity. Can AI really be creative? Selmer Bringsjord created a test for creativity he called the Lovelace test, named after the first computer programmer Ada Lovelace, who once said that, quote, "A computer has no pretensions to originate anything. It can do whatever we know how to order it to perform." The Lovelace test asks a simple question. Did the AI in question perform a task beyond the explanation of the person who wrote the AI code or someone with comparable expertise? If so, the Lovelace test is passed, and the AI is creative. Now, simply surprising results don't count. Bugs or results outside of expectation can be surprising, but they don't demonstrate creativity. When AlphaGo beat the world champion at Go, it made an unusual and surprising move that wasn't anticipated. This doesn't pass the Lovelace test because it was programmed to play Go, and that's what it did. You know what would have passed the Lovelace test? If AlphaGo all of a sudden started explaining the rules of chess, or if it started recommending you movies, all tasks outside of its training dataset. AI has not done and arguably cannot do anything beyond the explanations of its programmers, and therefore AI is not creative and AI superintelligence is unachievable. Currently, no one has successfully claimed a computer program has passed the Lovelace test, and you can read more about this in Roger Penrose's book, The Emperor's New Mind, where he argues creativity is non-computable and also links Gödel to Turing. Let's talk for a moment about the brain-computer analogy that's often offered in support of a physical reduction of the mind. This is a view called computer functionalism, which says basically that the mind is what the brain does, and the brain is basically a big old computer following computations or following instructions much like a computer. However, these brain-computer analogies break down quite quickly in a number of key ways. The first is that artificial neural networks are only very loosely inspired by actual biology. Not only do artificial or computational neurons differ in significant ways from biological neurons, but the way neural networks learn, if you can even call it that, is fundamentally different. For instance, consider what the father of AI and recent Nobel Prize winner Geoffrey Hinton said. Hinton popularized the backpropagation algorithms that's used to train multi-layer neural networks, and thinks backpropagation is not what's going on in our brains. He writes in a recent paper, quote, "As a model of how cortex learns, backpropagation remains implausible despite considerable effort to invent ways in which it could be implemented by real neurons." He continues, "There is no convincing evidence that cortex explicitly propagates error derivatives or stores neural activities for use in a subsequent backward pass." These analogies break down even further when we consider the philosophical problems with this brain-computer analogy. 19th century philosopher Franz Brentano asked a very important question. What is unique to mental states that is never found in matter? And the answer that he gave was intentionality. Now, intentionality is a philosophical term that means aboutness. Intentional things are inherently about something other than themselves. And all thoughts are intentional because they have an object to which they point. I can think about what I had for breakfast or about whether God exists. My thoughts are about something. However, physical objects are never about anything, except when we artificially attribute intentionality to them. A tree isn't about anything, it's just a tree. And a pencil isn't about anything, it's just a pencil. Physical objects just are what they are. Now, neurosurgeon and professor of surgery Michael Angor, who I also met at a conference recently, thinks intentionality is the fundamental problem with materialist theories of mind. He writes, quote, "Volumes have been written on materialist efforts to explain intentionality of the mind if the mind is material, and all have failed. The mind is not computation because it is always intentional, and computation is never intentional." And Angor goes so far as to say the mind is the antithesis of computation for this very reason. With that said, computer functionalism does make some sense, at least on the surface. We observe that by stimulating areas of the brain, we can cause people to move limbs and such. And as neurosurgeon Wilder Penfield, who pioneered the surgical treatment of epilepsy, famously observed, some seizures can cause people to have intense memories or emotions. However, while Penfield began his career as a materialist, he ended it as a passionate dualist, which basically says that there are some aspects of the mind that are not caused by the brain. Penfield had two reasons for this change of mind. The first is that there are no intellectual seizures. There are no seizures that can make you contemplate music or do a bunch of calculus. If someone tells you they couldn't stop doing a bunch of calculus, it wasn't a seizure, though they may have some other kind of problem. Now, noticing there are no seizures that evoke abstract thought, Penfield concluded that abstract thought does not originate in the brain. The second is that free will cannot be stimulated by the brain. Penfield prodded at people's brains while they were awake, also a procedure he pioneered, and of course found he could cause people to raise their arms and make other movements. And don't worry, this procedure is painless. The brain feels no pain and the scalp can be locally anesthetized. However, people always knew the difference between the movements they freely chose to do and those induced by the surgeon. Penfield could never find a region of the brain that stimulated free will. He thus concluded that free will is not in the brain, rather it is an immaterial power of the mind. However, there's an even more fundamental issue here, and it has to do with how we could in principle reasonably reduce the mind to the brain, even if we could cause abstract thought or the illusion of free will by poking at the brain. This example I for sure get from anti-flu. Now imagine a phone washes up on the shore of an island of cavemen. The cavemen get a phone call, presumably from the person who lost their phone trying to find it, and they wonder if there's a person on the other end of the phone. They decide to take it apart to find out if the voices coming out of the phone all originate from within the phone or if they come from something or somewhere external. They find that they can make sound come out of the phone's speaker by pressing certain buttons and prodding at it with tools, similar to deep brain stimulation. And some of the sounds that come out of the phone when they do this sound like voices. Furthermore, if they physically destroy parts of the phone no longer makes noises or appears to receive calls. Would they then be justified concluding there was nobody on the other side of the phone, or that all the sounds that come out of the phone originate completely from within the phone or from its inner workings? Of course not. And this is the fundamental epistemic limitation of any of these materialist brain analogies you often hear floating around that rely on these kinds of experiments. It's a non sequitur to conclude the mind is a computer because one can cause behavior by stimulating or destroying certain parts of the brain. And this is also a huge limitation of the Turing test, which we'll turn to now. Now, as discussed previously, what is called the Turing test was proposed by Alan Turing in his 1950 paper, Computing Machinery and Intelligence. In it, Turing proposes an imitation game. Suppose there's an observer C, a computer A, and another person B. Now, C is a conversation with the computer and the person, but isn't told who is who. Their job, C's job, is to decide which is the computer and which is the person. The computer's job, if you will, is to fool the person into saying they are the human. Now, while this is an interesting and important question, notice how Turing has reduced the idea of intelligence to simply intelligent behavior, or the mimicking of intelligent behavior. Whether the computer really thinks or reasons is irrelevant to winning the imitation game. Turing is no longer asking whether a machine can think. He is asking whether a machine can act indistinguishably from the way a thinker acts. As we saw from our island example, being able to induce or imitate a thing does not mean that's all there is to it. Now, Turing is correct to suggest that we typically determine others are intelligent through observation in a similar way. This is like the problem of other minds. But this is an epistemic limitation, not an ontological one. In other words, the fact that we infer intelligence in others based on their behavior does not mean this is the only relevant or even the most important part of intelligence. And it certainly doesn't answer the question of what gives rise to intelligence in the first place. Now, Turing himself was aware of this limitation and proposed his test as an empirical step in answering the question of whether machines can think. But today, you're going to come across a lot of people who do not understand this fundamental limitation and naively conclude machines can and do think based on the result of the Turing test. Some even go so far as to argue LLMs like ChatGPT are sentient or have real understanding of what they do, which many philosophers like the aforementioned Dreyfus or Searle would take a huge issue with for the reasons we discussed. Now, like I said earlier, I think ChatGPT can pass the Turing test, but it doesn't think or reason, at least not in the way that we do. In the end, AI is not, and probably never will be, sentient, creative, or have any understanding of what it does. If AI becomes dangerous, and there's a chance it could in the sense of how it is used socially, this will be the fault of the people who develop and use it. Computer ethics are important, which is why I've taught a university course in computer ethics the past several semesters on these kinds of topics. But a robot rebellion like the Terminator or the Matrix, yeah, that's science fiction. Anyway, here are the references. You can also find these in the description as well. Thanks for watching, and I will see you in the next video. In the end, AI is not, and probably never will be, sentient, creative, or have any understanding of what it does. If AI becomes dangerous, and there's a chance it could in the sense of how it is used socially, this will be the fault of the people who develop and use it. Computer ethics are important, which is why I've taught a university course in computer ethics the past several semesters on these kinds of topics. But a robot rebellion like the Terminator or the Matrix, yeah, that's science fiction. Anyway, here are the references. You can also find these in the description as well. Thanks for watching, and I will see you in the next video.